Hello. Today we're going to talk about topic 2.1, defining average rate of change and instantaneous rate of change at a point. Okay. So below, we're going to be talking about a variety of rates of change. And at the very top here, I have a sentence or two. It says the idea of average rate of change has many different names in calculus. Difference quotient is one way to say it. The slope of a secant line would be an average rate of change. And those are just two of the more popular ones. Okay, now in this little table, we have a lot of different ways we can express an average rate of change. Ultimately, it's going to be the change in your output values over the change in your input values. Okay. The ones that we'll take a look at specifically throughout this lesson are probably going to be the ones that I'm putting stars next to right now. Those three. But ultimately, all of those 6 boxes represent the same idea. Okay, so if you take a look at example 1, it says use the graph to write the answer of each question. I want the difference quotient from -6 to a +1, and those are x values. So if I go to the x value of -6, 2, 3, 4, 5, 6, right, and I put a point, and then I go to +1, and we're going to make that a nice point for our sake here. This is 6 comma 1, -6 comma 1, sorry. And this would be 1 comma 1, 2, 3, 4, 5, 6, -6. Okay, so if I find the average rate of change between those values, I would say -6 minus 1 all over a 1 minus a -6, which gives me a -7 over 7, or in this case, a -1. Okay. If you were to do part B, so let me change colors here. I want the slope of the secant line. So again, I just kind of the same type of question, just in a different wording. The slope of the secant line that passes through when x is 0. So we'll go when x is 0. So this looks like 0 comma -7. And 5. So for 5 is up here. This is going to be 5 comma 5. So if I find the slope of that secant line, I can say 5 minus a -7 all over a 5 minus 0. And I get 12 over 5. And I'm going to leave my average rate of change like that. Okay. No need to make a decimal if you don't need to. Okay. I want the average rate of change between 2 and 3. So if I go to 2, I'm right here. And if I go to 3, I'm right here. So at 2, I'm at 2 comma -4. And here I'm at 3 comma 0. So I can say the average rate of change would be a oops, wrong number. Okay, -4 minus 0 all over a 2 minus 3. And I get a -4 over -1, or in this case, a +4. Okay, so I ended up getting my 3 difference quotients, or slopes of the secants, or average rate of change. Again, I want you to be familiar with the different terminology. Okay. Okay, so I have a little box here at the bottom, just a little check for understanding. Explain what this difference quotient means. And there's a little hidden piece in the denominator here I want you guys to understand, because again, you're going to see this frequently. So I'm going to write in the bottom here that this denominator, before simplified, looked a little something like this. So if you reduce this, if I have f of -2 plus h minus f of -2 all over a -2 plus h, that would be a +2. The 2's would cancel, and I get f of -2 plus h minus f of -2 all over h. So what this finds is the average rate of change between -2, I'm going to use an x equals, between x equals -2 plus h and x equals -2, okay? So that's what we're finding with that type of difference quotient, all right? So I have a numerical example here, right? So the last one was graphical. So if I want to calculate the average rate of change between 1997 and 2002, feel free to pause the video. You can do this on your own. I'm going to use the values of 382, well, we'll say 12, comma 382. And in 1997, that would be 7, comma 62. So I'm going to say 382 minus 62 all over 12 minus 7. If you subtract that, we get a 320 all over 5. And if you divide 320 by 5, we'll get 64. Now, the thing that I want you guys to do on this is I want you to put the appropriate units. So I'm going to get 64 million people with email access per 1 year. Okay, so this is my average rate of change over the interval of 1997 to 2002. So it's 64 million people with email access per 1 year. Now, here's where you have to be very careful. If you were just to put 64 people per year, obviously that would be incorrect. We have to pay very, very close attention to what those units mean. Okay, so we're going to do the same thing for part B in 1998 to 2001. Okay, so that would be at 8, comma 130. And then in 2001 is 11, comma 313. So if I do 313 minus 130 all over 11 minus 8. So if I grab my calculator here, give me 1 second. I'm going to take 313 minus 130 gives me 183, and 11 minus 8 is 3. So if you take that 183 divided by 3, I get 61. Okay, so then I can say I have 61 million people with email access per 1 year. Again, this is a rate of change. This is the average rate in which it's changing, which the amount of people with email access is changing per year over that time interval, okay? So that's kind of the idea here. Now, what if I don't want the rate of change over an interval? I just want the rate of change at an instant, right? At 1 year or at one time. Okay, so that's what we're going to do. So what we're going to do is we're going to take this function, okay, I'm going to highlight it here for you, or bubble it, if you will, as soon as I can get my stylist connecting. There we go. Okay, so I'm going to take this function and we're going to apply this difference quotient, okay? But to do that, I want you to understand what h is. So I have a little activity here, and I'm going to use my calculator to kind of fill out this activity. What I'm going to do is I give you a point of 2, comma 3, right? So 2, comma 3 is my starting point. And what we're going to do is we're going to add a value to it, okay? And we're going to add, let's say we start with 1, right? And if I make that increasingly small, hold on a second here. If I make that increasingly small to like 0.1 or 0.01 or 0.001. And I keep getting smaller, right? We're going to essentially try to get 2 points that are incredibly or infinitely close to each other. So if I started at 2, if I add 1 to it, I'm going to be at 3. I'm going to be at 2.1, 2.01, 2.001, right? I'm just adding the original x value to my new h value. Okay, and I'm going to use my calculator to find the outputs at those points. So in my y equals menu, I'm going to put the 3x squared minus 5x plus 1, okay? And I'm going to go and I'm going to change my table to the ask feature so I can just type these in. So at 3, I'm at 13. At 2.1, I'm at 3.73. So you can already see a big difference here. At 2.01, I'm at 3.0703. Now, normally we can round to 3 decimal places in calculus. So that's what I'm going to do for these next few. I'm going to say this is 3.007. I'm going to say 2.0001. Keep going. So I got an extra 0 in there, and I have a feeling I'm going to get the same thing if I go one more. So I have 3.123 and a 1. Okay, so these are the output values. Now, what I'm going to do is I'm going to find the rate of change between my original point, the point that I know, and a point that's infinitely close to it, right? So I want to find the average rate of change between 2 comma 3 and a point that's infinitely close. So I'm going to say, and a point 2.00001, comma 3.1231, right? And this is going to give me an approximation of the instantaneous rate of change, and it's going to be my best approximation, right? If I have 2 points infinitely close to each other, that's going to be a pretty good idea of the slope of the graph at that point. So I'm going to say 3.1231, okay, minus 3 all over 2.12341 minus 2 equals. Oh, I'm doing it in my calculator now. So 3.123 1 minus 3 divided by 2.00001 minus 2. And I get the number of 10. Now, this is an approximation, okay? This doesn't give me an exact. Again, I could get infinitely closer. I could keep that h value getting smaller and smaller and smaller. And ultimately, the smaller it gets, the more exact my instantaneous rate of change will become, okay? So despite these good approximations, or despite using numbers very, very close together, we do have a method to get an exact value. And it follows the idea of limits, right? So as you can see from our table of values, the smaller that our h value got here, okay, the closer that our points are going to get together. Well, the idea is, well, if my h value can get to 0, right, then I'm ultimately using the same point. So what we're going to do is we're going to use these ideas, okay, and we are going to calculate the difference quotient, but I'm going to have this h value. So if you look at this first one, I'm going to have this h value go to 0. I'm going to have it get closer and closer to 0 using a limit rather than using a table of values. So here's how it works. So I'm going to start with my formula so you can see it. So I'm going to say the limit as h goes to 0 of, okay, f of x plus h minus f of x all over h. Okay, and I'm going to try and be as neat with this as possible. These tend to get a little long and messy. Okay, so I'm going to say the limit as h approaches 0. Now, f of x plus h. Everywhere where there's an x value, my input needs to change to an x plus h. So instead of a 3x squared, it needs to be a 3x plus h squared minus 5 times x plus h plus 1. Okay? Then I'm going to subtract. So this was the x plus h function minus the original function with just x as the argument. So it's just the original function all over h. Okay? So now I need to reduce this, and we did this way back in Unit 1. All right? So I am going to try to simplify this the best I can. And I'm going to start by squaring the binomial x plus h. So you'd have to write it twice, do all that distribution. Now, if you know the shortcut for squaring a binomial, it's the first term squared plus double the product plus the last term squared minus 5x minus 5h plus 1. Be very careful with your negatives. And then I'm going to still have a minus 3x squared minus 5x plus 1 all over h. Now I'm going to do a bunch of distribution here. I'm trying to change colors so you can follow my steps. As h approaches 0, if I do this, I get a 3x squared plus 6xh plus a 3h squared minus 5x minus 5h plus 1. Now I'm going to distribute the negative into the other function. All over h. Okay? And the fun part is now I can cancel things out, right? So if I do this, I know the 3x squareds cancel. 3x squared and negative 3x squared is 0. And then I have a, hold on, small mistake here. I forgot to distribute into the rest of my trinomial here, so I got to fix that. So it should be a plus 5x and a minus 1. Now, rule of thumb, if you do this right, almost always the terms in the function in the second half of your limit should cancel. So if you notice, the 3x squared, the 5x, the 1, those all cancel. So what I'm left with is the limit as h approaches 0 of a 6xh plus 3h squared minus 5h. You have to be nice and neat here, okay? Take your time. Make sure you don't miss any terms. All right? And now you can reduce an h from the numerator and the denominator. So if you factor out an h and cancel what's left, I get a 6x, because I canceled out an h, plus a 3h, again, I canceled out an h, minus 5. And now if we evaluate that limit as h goes to 0, I just get, oops, excuse me here, I get the expression 6x minus 5. Now, this is a very powerful expression here. This expression is actually what we refer to as a derivative. This function or this expression can find the instantaneous rate of change at any point. Now, the original question wanted the rate of change when x was 2. So if that's the case, I can just say 6 times 2 minus 5 gives me a 12 minus 5, so the rate of change would be 7. Okay, so that is my instantaneous rate of change. All right, now if you take a look at example 3, all right, we have a new quadratic. So what I'm going to do is I'm going to go through these. You can play the video, you can follow along, or you can pause before I start each one and you can try to do them. But I'm going to do this process, this limit process, for each of these three examples, okay? So feel free, like I said, if you need to pause it, please do so. But this is going to be a very skills procedural process where you have to pay attention to your negatives. So I'm going to start number 3, okay? I'm going to set up my formula. Again, I want to give you something for notes. So F, you could probably do this in less steps than me, but I want to make sure you have a good video to watch. All over H. So this is my difference quotient. So now I'm going to substitute in. Make sure you write your limit every time. X plus H squared minus 5 times X plus H minus 2. The original function is a negative 4x squared minus 5x minus 2 all over H. Change my colors. Limit is H goes to 0. I'm going to distribute a little bit. Negative 4 times x squared plus 2xh plus h squared minus 5x minus 5h minus 2. I can even distribute into the next piece the negative. So that would become a positive 4x squared, a positive 5x, and a positive 2. All over, trying to be nice and neat, H. Now I'm going to pick up at the top here. I'm going to distribute the negative 4. So I'm going to have here the limit as H goes to 0 of a negative 4x squared minus 8xh minus 4h squared minus 5x minus 5h minus 2. It's a lot of writing. Again, take your time. Plus 4x squared plus 5x plus 2 all over H. And the fun part, I'm going to cancel. So the negative 4x squared and the positive 4x squared, the negative 5x and the positive 5x, the negative 2 and the positive 2. So I have the limit as H goes to 0 of a negative 8xh minus 4h squared minus 5h all over H. I'm going to divide an H out of each term, which gives me a negative 8x minus 4h minus 5. Now, a very popular question is, well, what happens to the 4h? Well, when I substitute, I do my direct substitution of 0. Okay. I now get the, well, I don't need the limit anymore because I'm going to evaluate the limit. So this will give me a negative 8x minus 5. Okay, so this is the derivative. Okay, now I want to know what the slope is at x equals 3. So if I finish this problem off, so at 3, negative 8 times 3 minus 5 is a negative 24 minus 5. So I get a negative 29 is my instantaneous rate of change at that point. That's the slope of the line that crosses through that point. And specifically, it's the slope of the tangent line. But we'll get into that a little bit more. Okay? So if we go to number 4, all right, so another example. I'm going to start with my limit definition. As h approaches 0 of f of x plus h minus f of x all over h. So now I'm going to substitute in. So the limit as h approaches 0 of 7 times x plus h minus 4, and that's all under a radical, minus the square root of 7x minus 4 all over h. Okay, so what I want to do now is when I have these radicals, I need to use the operation of the conjugate. Okay, so I am going to multiply the top by 7x plus h. Excuse me there, I put a 4. X plus h minus 4. And then I would do a plus the radical 7x minus 4. So I'm using the conjugate. And you have to do the conjugate to both the top and bottom. Okay. Now the nice thing is when you distribute this conjugate, it's a difference of squares. So I'm going to just get the top part without the radical. You have to be very careful with your negatives here. So it's going to be the first expression without the radical minus the second expression without the radical. Again, because you just get each term squared over. Don't forget about that lonely h from the first denominator. And then on the bottom, I have this 7x plus h minus 4 plus the square root of 7x minus 4. Okay? Now, if we distribute, okay, trying to be as neat as I can here, so bear with me. The limit as h goes to 0 of, I have a 7x plus 7h minus 4, and then I have a minus 7x plus 4, because I distributed the negative, all over h times the square root of 7x plus h minus 4 under the first radical, and then plus the square root of 7x minus 4 under the second radical. And the fun part, the 7x and 7x cancel, the 4, negative 4, and the positive 4 cancel. Okay, so I'm going to write up top here. I'm going to say I now have the limit as h goes to 0 of a 7h over h times a lot of square roots. I know it's long. Plus the square root of 7x minus 4. Okay, so I just keep writing. All right, now when I do this, the h from the numerator cancels with the h of the denominator because they're both multipliers. And I'm left with the limit as h goes to 0 of a 7 on the top, the square root of 7x plus h minus 4 plus the square root of 7x minus 4. And if I let h go to 0, I am now going to, well, I guess I don't need my limit. If I'm going to let h go to 0, that's when you don't need your limit anymore. So I'm going to have a 7 over the square root of 7x plus h, which is 0, minus 4, plus the square root of 7x minus 4. Okay? And the way that I would write this, because those are both in the denominator and they're the same radical, is I would call this 7 over 2 times the square root of 7x minus 4, because I have two of them. Now, this would be my derivative, and if you let x equal 2, like you want it to be, I'm going to get 7 over 2 times the square root. 7 times 2 is 14 minus 4 is 10. And ladies and gentlemen, I would leave your answer like that. So this is the derivative. And then this is my instantaneous rate of change. So I abbreviated that, IROC. So again, instantaneous rate of change. Okay? So I have one more here. I'm going to switch over to green or something so you guys can see what's happening. Now, I'm also a little worried about space, okay? So I might go to the next sheet of paper here just to give myself some more room. But I have the limit as h goes to 0 of f of x plus h minus f of x all over h. And if I do this, I'm going to have the limit as h goes to 0 of 1 over x plus h plus 2 minus 1 over x plus 2 all over h. Okay, so this is what we call a complex fraction. So we did this in Unit 1 as well. So if I have a complex fraction, I need to get common denominators for my numerator. So when I do this, I'm going to have the limit as h approaches 0 of a 1 over x plus h plus 2. Let's make that nice and neat. Now I need to multiply this by an x plus 2 and an x plus 2. Minus 1 over x plus 2, and I need to multiply this by an x plus h plus 2, and this by an x plus h plus 2. And that is all over h. Again, trying to get common denominators in the numerator. So now I have an x plus 2 over x plus h plus 2 times x plus 2 minus 1 times x. Well, I guess I don't really need the 1, right? So let's do that without the 1. I don't want to make more steps than necessary. All over x plus 2, x plus h plus 2. And then don't forget about that lonely h in the denominator. It's always there, okay? So now if I combine these fractions together, I get the limit as h approaches 0 of x plus 2, and I'm going to distribute the negative, minus x minus h minus 2. Again, we're subtracting that fraction, so everything in the numerator gets a negative. X plus h plus 2, x plus 2. The fun part, let's cancel. X's go away, 2's go away. Now be very careful here because I now have the limit as h goes to 0 of a negative h on top. Don't lose that negative. It's a minus h, remember? So it's still negative over x plus h plus 2, x plus 2. If I evaluate that limit as h goes to 0, I now have, oh, you know what I forgot? Silly me, I even warned you for it. This should be all over h, right? So let me go back a step. Okay, I forgot to put my h denominator. Okay, so when I do that, because this is all over h, I'm going to multiply by the reciprocal. So let me show that. Sorry about that, guys. Got a little too fast. X plus h plus 2, x plus 2. Now, when I multiply by the reciprocal of the denominator, you'll see that also the h's cancel. I still do have a negative 1 on the top, though. That looks better. And now if I evaluate that limit, I get a negative 1 over x plus h, which h is 0, so just be an x plus 2. And I also have an x plus 2. So I would call this a negative 1 over x plus 2 squared. This is my derivative. Okay? And if I want to figure out, we wanted the average or the instantaneous rate of change at negative 5. So when x equals negative 5, my instantaneous rate of change is going to be a negative 1 over negative 5 plus 2 is negative 3 squared, 9. So my instantaneous rate of change is a negative, 1/9, where my derivative was that function above. Okay, I know that these problems take a little bit of time, and the quicker you get with your algebra, okay, the faster that they'll go. Obviously, polynomials are a lot easier to work with. Radicals, we have to use that conjugate. And then when you have a rational function, we have to deal with common denominators. Okay, so that's kind of the idea. I hope this helped. Feel free to email me, ask me any questions if you need them, and have a good day.